I want to start by saying that what James Webb is discovering in the distant universe isn't matching up with what scientists thought they understood. Some of the most luminous sources in those incredibly deep observations aren't acting like the infant galaxies researchers predicted. They're displaying spectral characteristics that seem completely wrong for their supposed age, and their luminosity doesn't align with how rapidly structure should have assembled in that era. Because of this mismatch, a small group of researchers are raising a question that sounds deceptively straightforward, but carries profound implications. What if these primordial sources aren't galaxies in any conventional sense? What if something else emerged before galaxies even had the opportunity to coalesce? Something driven by a mechanism we've never witnessed operating in nature. Dark matter stars, sometimes simply called dark stars, represent a theoretical class of stellar object hypothesized to have existed in the universe's infancy roughly 200 to 500 million years following the Big Bang. Unlike conventional stars that generate light through nuclear fusion reactions in their compressed cores, dark stars would derive their energy primarily from the mutual annihilation of dark matter particles. Their composition would be predominantly ordinary matter, approximately 75% hydrogen and 25% helium drawn from the primordial cosmic gas, but they would harbor a minuscule fraction of dark matter, typically less than 1% by mass. This dark matter component is generally assumed to consist of weakly interacting massive particles, such as neutralinos that emerge from certain supersymmetric extensions to the standard model of particle physics. Most people envision a star as an enormous sphere of gas compressed so intensely that the internal pressure forces atomic nuclei to fuse together, releasing tremendous amounts of light and thermal energy. That's the standard picture that governs every star we observe in the night sky today. But dark stars, a theoretical framework first articulated in 2007 by astrophysicists Catherine Fries, Douglas Spoliar, and Paolo Gondolo, present an entirely different mechanism for stellar luminosity. Consider a region of space densely populated with dark matter, where individual particles can annihilate upon encountering their antiparticles. When these annihilation events occur, they don't produce sudden violent explosions. Instead, they generate a continuous, gentle release of thermal energy. In a dark matter star, this sustained energy output from particle annihilation, rather than thermonuclear fusion, becomes the dominant power source maintaining the object's luminosity and internal pressure support. In the primordial universe, when cosmic structure was still in its earliest stages of formation, dark matter naturally concentrated in locations where gravitational forces were most intense. These gravitationally bound concentrations formed the first dark matter halos, serving as the gravitational scaffolding upon which galaxies would eventually assemble. The central regions of these halos achieved sufficient density that dark matter particles collided with significantly higher frequency. If dark matter particles belong to a class that self-annihilates upon contact with their corresponding antiparticles, each collision releases a small but measurable quantity of energy. The energy release per individual particle interaction might seem negligible, but the early universe contained vast reservoirs of dark matter packed into extraordinarily compact volumes. This steady injection of thermal energy could fundamentally alter the collapse dynamics of a primordial gas cloud, preventing it from contracting into a conventional protostar on normal timescales. Instead of compressing into a dense, compact sphere like our Sun, the cloud maintains a much looser, expanded configuration. It swells outward. The object becomes a large, relatively cool structure, where the outward thermal pressure generated by dark matter heating precisely counterbalances the inward gravitational compression. Because thermonuclear fusion hasn't yet ignited in the core, the central temperature never reaches the extreme values characteristic of ordinary stars. The surface temperature remains cool enough that these objects would radiate predominantly in the infrared portion of the electromagnetic spectrum. They wouldn't appear as the brilliant, compact points of light we associate with normal stars today. Instead, they would manifest as diffuse, extended sources, almost resembling luminous spheres composed of gently heated gas. What makes this theoretical framework particularly intriguing is the potential scale these objects could achieve. Without the intense radiation pressure and core compression associated with fusion reactions working to destabilize the structure, nothing inherently limits their mass accumulation. They could continue accreting hydrogen and helium from their surrounding environment, steadily growing over timescales spanning thousands or potentially millions of years. Some computational models suggest they could reach masses that sound almost absurd by conventional stellar standards. Millions of solar masses, with physical diameters exceeding those of entire planetary systems. Not dense, like a neutron star. Not searingly hot, like a blue supergiant. Just extraordinarily large and faintly glowing. More accurately described as cosmic balloons, with a gentle internal heating mechanism rather than traditional stars. This unusual energy source also fundamentally changes their evolutionary timescales and longevity. A conventional massive star consumes its nuclear fuel with tremendous rapidity and undergoes catastrophic collapse relatively quickly on cosmic timescales. But a dark matter star doesn't initially depend on fusion reactions for its luminosity. It can exist in this peculiar quasi-static state for extended periods. Its lifetime becomes determined by the local dark matter density and the rate at which that reservoir of annihilating particles gets depleted. If the supply of dark matter remains relatively constant and replenishes through ongoing gravitational accretion, the star could persist far longer than a fusion-powered star of equivalent mass would survive. This extended lifetime means the object could continue growing, radiating energy, and dominating its local environment, all while waiting for the inevitable moment when the dark matter fuel supply finally becomes exhausted. And when that depletion occurs, the entire structure undergoes a dramatic transformation. Without the stabilizing thermal support from dark matter annihilation, the object can no longer resist its own immense gravitational field. It collapses rapidly under its accumulated weight and either finally initiates thermonuclear fusion in its core if conditions permit, or collapses directly into a supermassive black hole if the mass has grown sufficiently extreme. This potential outcome represents a crucial element of why researchers take the dark star hypothesis seriously despite its exotic nature. If early dark matter stars existed in even modest numbers throughout the primordial universe, they could seed the formation of black holes vastly more massive than any conventional stellar collapse could possibly produce. Those remnant black holes would then provide a natural explanation for one of modern astronomy's most perplexing observations: why the James Webb Space Telescope keeps detecting quasars and other extremely luminous active galactic nuclei at astonishingly early epochs in cosmic history, times when standard formation models suggest such massive black holes simply shouldn't exist yet. At this stage in the scientific discourse, dark matter stars remain a well-developed theoretical hypothesis supported by detailed numerical simulations of stellar structure and evolution. But the underlying physics doesn't require wildly speculative assumptions or revolutionary new laws of nature. The concept relies on just two ingredients that many physicists already expect to exist based on independent lines of evidence. First, dark matter must form gravitationally bound, high-density concentrations in the early universe, which is a natural consequence of standard cosmological structure formation. Second, certain theoretical candidates for dark matter particles must be capable of releasing detectable energy when particle-antiparticle pairs encounter each other and annihilate. Combine both ingredients in the appropriate astrophysical environment, and you naturally produce a stellar mass object that doesn't behave like any star in the contemporary universe. A giant, slowly radiating structure that shines for reasons we've never directly observed in nature before. If such objects formed within the earliest dark matter halos, they wouldn't remotely resemble the stars populating galaxies today. They would be dramatically larger, significantly cooler, substantially dimmer when observed in visible light wavelengths, and considerably brighter when viewed in the infrared portion of the spectrum. And because the James Webb Space Telescope was specifically designed to observe the universe at infrared wavelengths with unprecedented sensitivity, it represents the first astronomical instrument with the technical capability to potentially detect something matching this theoretical profile. Several independent research teams have identified specific high redshift objects in JWST datasets as plausible dark star candidates, triggering intense scientific debate and motivating extensive follow-up observational campaigns. Whether Webb has already detected these objects, or will conclusively confirm or rule them out in upcoming observations, forms the core of what makes the current scientific controversy so compelling. When the first deep-field images from James Webb began arriving in astronomical databases, researchers anticipated seeing small, faint sources representing the cosmic dawn, objects that had barely begun assembling mass, systems that would require substantial time to develop into recognizable galaxies. But instead of confirming those expectations, Webb started identifying sources that violated multiple theoretical predictions simultaneously. Some of these detected objects exhibited extraordinary luminosity, despite residing at cosmological distances indicating the universe was merely a few 100 million years old when their light was emitted. That combination of brightness and extreme age doesn't align with what early galaxy formation models predict should exist. The timescales simply don't provide sufficient opportunity to assemble that much radiating mass through conventional processes. One of the initial surveys where this anomaly became apparent was the JADES program, the JWST Advanced Deep Extragalactic Survey. Webb wasn't specifically targeting dark matter stars or searching for exotic theoretical objects. The telescope was simply conducting deep imaging of a carefully selected region of sky with maximum sensitivity across multiple infrared wavelengths. Within that surveyed region, several sources immediately stood out as anomalous to experienced observers. They appeared compact when measured by their angular extent on the sky, yet their total integrated luminosity seemed far too intense given their apparently small physical size. Normally, when astronomers detect a compact luminous source at high redshift, they expect to classify it as either a young starburst galaxy experiencing extremely rapid star formation, or possibly an actively accreting black hole consuming surrounding material at high rates and converting that accretion into intense radiation. But when spectroscopic observations broke down the light from these peculiar objects into their component wavelengths, the resulting spectra didn't cleanly match either standard interpretation. Instead of displaying the characteristic spectral signatures pointing toward large populations of hot, young, massive stars undergoing vigorous fusion, the light exhibited a smoother continuum, with a more blackbody-like character and cooler effective temperatures than anticipated. The spectrum showed a broad, thermal glow consistent with something substantially cooler and more extended than expected. This seems strange because early galaxies dominated by massive star formation should produce copious amounts of high-energy radiation, strong emission lines from ionized gas, and numerous other energetic spectral features. These anomalous objects lacked several of the diagnostic signatures that would straightforwardly confirm their identity as conventional early galaxies. That's when certain research groups began comparing the observational data against theoretical models that most astronomers never seriously expected to test against real observations. The predicted spectral energy distribution of a dark matter-powered stellar atmosphere. These theoretical models predict a distinctly different spectral shape compared to galaxies. A dark matter star would radiate primarily in infrared wavelengths with a smoother, softer spectrum, lacking the sharp features characteristic of stellar populations. And when preliminary comparisons were performed, some researchers noted that the agreement wasn't terrible. In several specific cases, the dark star models actually fit the observed photometry and limited available spectroscopy better than standard galaxy templates, even when those templates were adjusted to extreme parameter values. That correspondence alone doesn't constitute proof of anything, but it proved sufficient to capture serious scientific attention and motivate deeper investigation. The physical sizes added another layer to the puzzle. When scientists calculated how physically large these early objects would need to be based on their measured distances and observed angular sizes, accounting for cosmological expansion, they didn't find tiny, dense star clusters. They didn't discover compact proto-galaxies packed with superhot stellar populations. Instead, the inferred sizes were substantially larger and more diffuse than theoretical expectations, matching reasonably well with what numerical simulations predicted for supermassive dark stars once adjusted for JWST's observational resolution limits and selection effects. Not large enough to immediately declare the discovery of something definitively exotic, but unusual enough to make experienced researchers pause and fundamentally reconsider what they were observing. These were objects radiating with an intensity that didn't easily reconcile with their inferred age, mass, or structural properties under standard assumptions. Another troubling aspect was that some of these sources appeared to exist before the universe had experienced enough elapsed time to construct them through normal astrophysical processes. Galaxy formation requires extended periods to gravitationally collect diffuse gas, initiate star formation, undergo hierarchical merging events, and gradually build up substantial stellar mass. But some of the JADE's objects would need to have accumulated their observed luminosity incredibly rapidly, unreasonably fast by conventional standards. That severe timing constraint made astronomers wonder whether these objects had received some form of assistance, some alternative formation pathway that allowed them to achieve high luminosity very early without progressing through the standard sequential stages of galaxy assembly. The particularly interesting aspect is that Webb wasn't revealing a single isolated anomaly that could be dismissed as a measurement error or statistical fluke. Multiple objects were being identified that shared similar combinations of unusual properties: high luminosity, compact appearance, and unexpected spectral characteristics. They weren't identical to each other, but the constellation of peculiar traits kept appearing across independent detections. That consistency across multiple objects is what gives the dark star interpretation a meaningful foothold in serious scientific discourse. If the observational oddities repeat systematically across numerous sources, it forces the scientific community to seriously consider that they might not all represent simple modeling uncertainties or rare exceptional cases requiring ad hoc explanations. So at this juncture in the investigation, the situation became straightforward to articulate but challenging to resolve. Webb had detected objects that didn't fit comfortably into the established classification frameworks astronomers normally employ for early universe sources. They appeared too luminous for their age, too early in cosmic history to have assembled conventionally, and their spectral energy distributions didn't behave the way early galaxies typically behave according to established theoretical models. Several research teams performed detailed quantitative analyses and discovered that dark star models could account for these combined observational traits with surprising fidelity. That agreement doesn't prove the dark star hypothesis is correct, but it opened a theoretical door that most researchers didn't anticipate would even merit serious consideration. And that possibility proved sufficient to initiate an intense scientific debate, not because anyone deliberately set out to discover dark matter stars as a research objective, but because some of Webb's earliest deep-field observations forced astronomers to genuinely question whether the first self-luminous objects emerging in the infant universe were something fundamentally stranger and more exotic than the stars and galaxies we thoroughly understand from observations of the contemporary cosmos. As additional observational data from Webb continued accumulating following the initial public data release, the catalog of anomalous objects didn't diminish as one might expect from improved measurements, clarifying initial confusion. Instead, the list slowly expanded. New detailed studies utilizing deeper Webb observations succeeded in identifying 4 particularly strong candidates for objects potentially representing dark stars. 2 of the most scientifically interesting candidates were designated JADES GSZ140 and JADES GSZ141. Both objects were observed at a redshift of approximately 14, meaning the light we're currently detecting was emitted when these sources existed only roughly 300 million years after the Big Bang, during an extraordinarily early epoch in cosmic history. One particular object, JADES GSZ140, attracted substantial scientific attention and scrutiny. Its spectrum exhibits a subtle but potentially significant absorption feature, a small dip in the continuum flux, near a rest frame wavelength of approximately 1,640 angstroms. This spectral feature carries considerable importance because that specific absorption signature is precisely the kind of diagnostic signal that certain theoretical models predict a supermassive dark matter star should produce in its spectrum. This particular feature isn't expected to appear in normal early galaxies composed of population 3 stars formed from primordial gas, nor in stellar populations synthesized from the universe's first generation of metal-free elements. In detailed dark star theoretical models, this absorption feature naturally emerges when photons emitted from the luminous interior pass outward through an enormous, cool, extended gaseous envelope surrounding the central energy source. A structural component that conventional fusion-powered stars simply don't possess at comparable scales. It represents a signature of the object's fundamental physical structure and atmospheric composition rather than merely its total integrated luminosity or color. In straightforward terms, if you constructed a detailed model of a giant non-fusion stellar object possessing a thick atmospheric layer gently heated by dark matter particle annihilation rather than nuclear burning, theoretical calculations predict you should observe something closely resembling that absorption dip appearing in the emergent spectrum. When research teams compared their best-fit dark star models directly to the observed spectroscopic data, the level of agreement was close enough to generate considerable interest and discussion within the astrophysics community. However, a significant challenge exists with interpreting this feature. The signal strength isn't particularly robust. It sits precariously close to the detection threshold of what Webb can reliably measure for sources this intrinsically faint and cosmologically distant. With that marginal level of statistical significance, some skeptical scientists argue the feature might simply represent instrumental noise, calibration artifacts introduced during data reduction, or random fluctuations in the background, signal that happen to mimic a real spectral feature. Other researchers counter that even if the absorption feature is genuinely astrophysical in origin, there exist plausible mechanisms by which certain types of early starburst activity or unusual stellar populations could potentially create superficially similar spectral signatures without requiring exotic dark matter physics. That fundamental disagreement about interpretation is precisely why the scientific debate hasn't converged on a single consensus explanation despite extensive analysis. Beyond that, one potentially diagnostic spectral detail, the broader observational pattern emerging from the data, is that dark star theoretical models appear to fit several of the newly identified candidates somewhat better than standard early galaxy templates across multiple independent observational diagnostics. When you attempt to explain a compact, extremely luminous high redshift source using conventional early galaxy models, you frequently need to adopt parameter values that push the models into physically uncomfortable or implausible regimes. Extraordinarily high stellar densities, extreme and sustained star formation rates far exceeding what local analogs exhibit, or contrived scenarios involving highly specific evolutionary histories that feel artificially constructed to match the observations. But when those identical observational datasets are tested against theoretical predictions for dark stars, the model fits can be substantially smoother and require fewer ad hoc adjustments to free parameters. This doesn't definitively prove the dark star interpretation is the correct physical explanation, but it clearly demonstrates why certain research teams believe the hypothesis merits serious continued investigation rather than immediate dismissal. Another consideration researchers emphasize is how the population statistics of these anomalous objects behave as observational surveys probe progressively deeper into the dataset and cover additional independent fields. If the strange sources represented merely rare statistical outliers or isolated exceptional cases, you wouldn't reasonably expect to continue discovering them repeatedly in different sky regions surveyed at comparable depths and sensitivities. Yet these peculiar objects keep appearing in follow-up surveys targeting different coordinates, not in overwhelmingly large numbers that would suggest they dominate the early universe, but frequently enough to establish what appears to be a genuine population rather than accidental coincidence or systematic measurement error affecting a single field. Patterns matter profoundly in observational astronomy. They compel theoretical frameworks to either successfully adapt and accommodate new phenomena, or step aside for alternative explanations. None of this accumulated evidence definitively proves that dark matter stars have been successfully detected and confirmed. Every individual piece of observational evidence presented thus far possesses at least one alternative conventional explanation that could potentially account for the observations without invoking new physics or exotic stellar types. But the combination of factors, the unusual luminosity to age ratios, the peculiar spectral energy distributions, the growing number of morphologically similar candidates, and the tentative atmospheric absorption signature collectively keeps the theoretical door open for continued serious investigation. The more extensively Webb surveys the high redshift universe, the more frequently these anomalous objects appear in regions where early galaxy populations are supposed to be relatively straightforward to interpret using established models. That persistent tension between observation and theoretical expectation is what fundamentally drives the current scientific argument. Some researchers interpret this as an increasingly compelling sign that dark matter stars might finally be directly observable with modern instrumentation. Others view the same evidence as a healthy challenge motivating galaxy formation models to become more sophisticated, flexible, and physically realistic when applied to the extreme conditions of the early universe. Right now, the preponderance of evidence occupies an uncomfortable middle ground that characterizes many active scientific controversies. Intriguing enough to warrant serious discussion at conferences and detailed investigation in peer-reviewed publications, but not yet solid enough to claim anything approaching definitive confirmation or consensus acceptance. And that ambiguous evidential status is exactly why numerous scientists across multiple institutions are closely monitoring the next generation of Webb spectroscopic observations with considerable anticipation. A substantially clearer, higher signal-to-noise detection of diagnostic spectral features from any single one of these candidates could potentially settle the fundamental question decisively, either confirming the dark star interpretation or revealing an entirely different physical explanation that nobody is currently anticipating. As soon as the dark star hypothesis gained traction in professional astronomical literature and broader scientific discussions, substantive criticism and pushback emerged with comparable speed. A significant fraction of astronomers remain firmly convinced these unusual Webb objects can be comprehensively explained without introducing anything exotic or invoking physics beyond the standard model. Their fundamental argument is straightforward and methodologically conservative. Early galaxies formed under radically different environmental conditions than galaxies in the contemporary universe, so it's entirely plausible and perhaps even expected that they exhibit observational properties that appear anomalous when analyzed using models calibrated primarily on nearby, well-studied systems. Critical voices in the debate, including prominent researchers such as Daniel Whalen and Julian Munoz, suggest that conventional astrophysical explanations, like exceptionally massive early stellar populations, direct collapse black hole formation scenarios, or extraordinarily intense star formation episodes confined to very small, compact galactic regions, can successfully reproduce many of the same observational signatures currently attributed to potential dark stars, all without requiring any modifications to known physics. If the universe's first galaxies formed stars at rates substantially higher than current models predict as typical, or if nascent galaxies achieved much higher stellar densities than previously assumed feasible, they could potentially produce the extreme brightness Webb is detecting without needing dark matter particle annihilation as an additional energy source. Critics also highlight a fundamental problem confronting the dark star hypothesis from the particle physics perspective. The specific process hypothesized to power these objects, weakly interacting massive particles, mutually destroying each other upon contact, has not been conclusively detected in any terrestrial laboratory experiments despite decades of increasingly sensitive searches, nor has it been unambiguously observed in gamma-ray observations of astrophysical environments, where dark matter concentrations should be highest. The lack of independent confirmation for this specific dark matter interaction mechanism represents a significant theoretical weakness. Because of this absence of direct detection, many physicists are increasingly exploring alternative dark matter candidates, such as axions or other particles that don't self-annihilate, which would entirely eliminate the energy generation mechanism required for dark stars to exist. One of the most commonly proposed conventional explanations for the anomalous Webb observations involves compact starburst regions operating at extreme intensity. These represent localized pockets of extraordinarily vigorous star formation where hundreds of thousands or potentially millions of new stars are forming rapidly within a relatively confined spatial volume. If such intense starburst activity occurred commonly in the early universe, The integrated light emerging from those regions would be extremely strong and spectrally complex, which might obscure or blur many of the diagnostic spectral features astronomers normally rely upon to accurately characterize and classify young galaxy populations. This spectral complexity could make early starbursts appear smoother or exhibit cooler effective color temperatures in their integrated light than the underlying stellar populations actually possess, potentially mimicking some observational characteristics attributed to dark stars. Another alternative explanation points toward rapidly accreting supermassive black holes as the luminosity source. If certain early proto-galaxies somehow managed to form central supermassive black holes that began accreting surrounding gas at extremely high rates very early in cosmic history, the intense radiation emitted from the superheated accretion disk and surrounding material would produce a qualitatively different spectral signature than stellar populations. This accretion-powered emission can flatten and smooth the overall spectral energy distribution, making the source appear less characteristic of a normal star-forming galaxy dominated by hot young stellar populations. It might even suppress or dilute certain spectral emission lines, and features researchers expect to prominently appear in early galaxies powered purely by stellar processes. In this alternative scenario, the unusual light signatures aren't originating from a giant, dark matter-powered, quasi-stellar object. Instead, they're being produced by ordinary matter, falling into a black hole that's somehow growing faster and earlier than standard formation models previously assumed physically possible given the available timescales. There's also the methodological possibility that the theoretical models and spectral templates used to interpret these distant objects aren't yet sufficiently refined or comprehensive. A substantial fraction of the galaxy templates astronomers routinely employ to understand observations of high redshift sources were originally constructed and calibrated before Webb existed and began returning data. Those models were based on extrapolations from lower redshift observations and theoretical expectations that hadn't been tested against direct observations of the actual early universe. Once Webb started delivering substantially clearer, higher quality data at unprecedented redshifts, some of those pre-existing theoretical models didn't perform as reliably as anticipated when applied to these extreme observational regimes. Because of that growing recognition of model limitations, some researchers argue compellingly that the apparent mismatch between theoretical predictions and observational measurements isn't necessarily evidence supporting the existence of a fundamentally new type of astrophysical object. Instead, it might simply be a clear indication that the analytical tools, spectral synthesis codes, and theoretical frameworks used to physically describe and interpret early galaxies require substantial updating, refinement, and recalibration in light of new observational constraints. In other words, the core problem might not reside in the galaxies themselves exhibiting exotic properties. The problem might lie primarily in the inadequacy of the interpretive tools currently being applied to describe them. Measurement uncertainties and observational challenges also play a non-trivial role in the controversy. When dealing with astronomical sources this intrinsically faint and located at such extreme cosmological distances, even relatively small systematic uncertainties in photometric measurements or spectroscopic calibration can dramatically change the physical interpretation of the observations. A modest systematic error in estimating the physical size, total mass, or stellar mass-to-light ratio of an object can shift the preferred interpretation from unusual galaxy to plausible dark star candidate, and back again, depending on which specific assumptions are adopted. The same methodological sensitivity applies to decomposing and analyzing spectral energy distributions. If the observed signal approaches the instrumental noise floor, the detailed shape of the spectrum can be influenced by random noise fluctuations, systematic calibration uncertainties, or subtle instrumental artifacts that aren't immediately obvious during standard data reduction procedures. Some astronomers emphasize that until measurement precision improves substantially through longer integration times or observations with complementary facilities, these subtle observational details shouldn't be overinterpreted as definitive evidence of something fundamentally new and exotic. Even confronted with all these substantive counterarguments and alternative explanations, Not everyone in the astronomical community remains convinced. The traditional interpretations adequately account for everything Webb is revealing. A persistent minority of researchers continue noting that the specific combination of observational features, high luminosity at very early epochs, compact morphological appearance, and unusual spectral characteristics, keeps recurring across multiple independent detections in a way that seems difficult to dismiss as pure coincidence. If the anomalies were restricted to a single isolated object, it would be scientifically reasonable and methodologically appropriate to dismiss it as a measurement error, calibration problem, or rare statistical fluctuation. But observing several independent sources, exhibiting similar constellations of unusual traits, compels these researchers to keep the theoretical door open for unconventional explanations, rather than prematurely closing off investigation. They're not claiming dark stars must definitively be real, or that the hypothesis has been proven beyond reasonable doubt. They're simply arguing that the conventional early galaxy explanation still leaves certain observational gaps and tensions unresolved, and that alternative hypotheses deserve continued serious investigation until definitively ruled out by compelling evidence. This fundamental disagreement about how to weight and interpret ambiguous evidence is precisely what makes the ongoing debate so scientifically active and productive. Both sides present intellectually reasonable positions supported by legitimate arguments. The skeptical faction wants existing models to be systematically updated, observational measurements to improve in precision and signal-to-noise, and measurement systematics to be thoroughly characterized before seriously entertaining new physics or exotic object classes. The researchers maintaining openness toward dark stars believe the emerging pattern of strange objects exhibits too much internal consistency to completely ignore, and that prematurely dismissing the hypothesis without adequate investigation would represent poor scientific methodology. Neither perspective currently possesses definitive evidence strong enough to completely eliminate the opposing viewpoint because the available observational data simply isn't yet detailed or comprehensive enough to settle the controversy decisively. Right now, the scientific debate occupies a productive middle ground characteristic of healthy scientific discourse. Dark stars remain a viable theoretical option worth investigating, but certainly not the only possibility or even necessarily the most probable explanation. Early galaxies could genuinely be far more extreme, diverse, and physically complex than theoretical models developed before Webb anticipated. Black holes might be growing substantially faster through mechanisms not yet fully understood. Spectral synthesis models and galaxy templates might require major revision when applied to the earliest cosmic epochs. Or there could exist a heterogeneous mix of explanations where different anomalous objects fall into distinct physical categories, requiring different interpretations. The only aspect that seems certain at this stage is that Webb has revealed portions of the early universe that aren't nearly as straightforward or well understood as scientists confidently thought before these observations became available. When the next generation of high-resolution Webb spectroscopic observations arrives from approved observing programs specifically designed to address these questions, many of these competing theoretical ideas will face more direct and stringent empirical tests. If the unusual spectral features become substantially clearer and more statistically significant with improved data quality, the scientific conversation will shift accordingly and potentially converge toward consensus. If apparent anomalies disappear or become explicable under better data quality and more sophisticated analysis, the dark star hypothesis may gradually fade from serious consideration. For now, both interpretive camps are analyzing the same observational signals and reaching substantively different conclusions, each waiting for the critical piece of evidence that finally tips the scientific balance decisively. The reason people throughout the astrophysics community care deeply about this theoretical idea isn't primarily because it sounds intellectually strange, or because it provides an opportunity to bring dark matter into the observational spotlight after decades of indirect inference. The genuine scientific interest stems from what these hypothetical objects could potentially solve. For many years, astronomers have struggled with several persistent problems and tensions that didn't align cleanly with theoretical expectations, especially when examining the earliest developmental stages of cosmic structure formation. Webb made those pre-existing problems substantially clearer and more acute rather than resolving them as some optimistically hoped. Some of the first galaxies Webb has detected appear significantly brighter and more massive than theoretical models predict they should be given their young age and the limited time available for mass assembly. And compounding that puzzle, we already know from previous observations that extremely massive black holes, containing millions or even billions of solar masses, exist at surprisingly early epochs, long before the universe experienced sufficient elapsed time to plausibly build them through conventional processes involving stellar death and gradual accretion. If dark matter stars existed in the early universe, even in relatively modest numbers rather than dominating the stellar population, they would offer an elegantly simple pathway through these observational difficulties. Because they grow slowly and steadily through continuous accretion rather than explosive processes, they could reach truly enormous masses without becoming dynamically unstable or evolving into short-lived, rapidly evolving objects. They could continue steadily gathering material from their surrounding environment for timescales far longer than typical early star clusters or stellar populations could maintain coherence. And because they aren't initially powered by thermonuclear fusion reactions, they completely avoid the intense internal radiation pressure spikes that normally prevent stars from growing beyond certain mass thresholds before becoming unstable. All of these unusual properties allow them to become absolutely huge while remaining relatively quiescent and stable. When the dark matter heating mechanism finally fades, as the local particle reservoir becomes depleted, their already enormous accumulated mass means they can collapse directly into black holes, vastly more massive than anything a conventional stellar collapse could possibly produce, even from the most massive fusion-powered stars known. Those remnant black holes could then serve as the initial seeds for the earliest quasars and active galactic nuclei, the exact population of extreme objects. Webb is already detecting at distances, indicating they formed at cosmologically early times. Instead of requiring black holes to start from a few dozen solar masses produced by normal stellar death and then slowly gaining mass through prolonged accretion, they could begin their existence already containing tens of thousands, or conceivably even millions of solar masses. That kind of substantial initial mass advantage fundamentally changes everything about subsequent growth timelines. It completely eliminates the need to invoke unusual super-Eddington accretion rates, extraordinarily efficient feeding mechanisms, or highly contrived extreme environmental conditions to explain how early supermassive black holes managed to reach their observed enormous sizes so quickly. There's also the persistent question of why certain early galaxies detected by Webb appear too intrinsically bright for their inferred age and evolutionary state. If some fraction of the luminosity Webb is detecting originates not from conventional stellar populations in star clusters, but instead from dark matter-powered objects radiating through an entirely different physical mechanism, that would fundamentally shift the interpretation of those brightness measurements. A dark star would possess a completely different internal structure, effective temperature profile, and spectral energy distribution compared to a compact cluster of young fusion-powered stars. If even a modest portion of the early luminous sources contributing to Webb's detections represents objects like these, rather than normal stellar populations, the total stellar mass estimates for those early galaxies would require substantial downward revision. They might not actually be as intrinsically massive as initial interpretations suggest, based on assuming all luminosity originates from conventional stars. They might simply contain luminous components that standard galaxy models were never designed to include or account for. Another significant impact lies in how we conceptually understand the timeline and sequence of cosmic structure growth. Right now, the standard cosmological picture describes galaxies forming through a gradual, relatively predictable hierarchical process, with small dark matter halos and gas clouds merging progressively into increasingly larger structures. Webb's early observational findings challenge that orderly picture by revealing objects that seem to have jumped significantly ahead of the expected evolutionary sequence. A dark matter star phase would effectively act as a transitional bridge connecting the small, primordial dark matter halos, characterizing the very early universe with the surprisingly mature luminous systems Webb is detecting at high redshifts. It doesn't completely rewrite the entire narrative of cosmic structure formation, but it would fill in problematic gaps and smooth over tensions that have proven persistently difficult to explain using conventional galaxy formation physics alone. For theoretical physicists working on dark matter, the idea also offers a genuinely new avenue to empirically test dark matter particle physics in ways that go beyond purely gravitational effects. Dark matter remains predominantly invisible and mysterious to us, despite overwhelming evidence for its gravitational influence. We know with high confidence that it gravitationally shapes cosmic structure on large scales, but we typically don't get opportunities to observe it interacting or doing anything directly observable beyond its gravitational effects. If dark stars are real and successfully detected, they would represent a scenario where dark matter particles interact with ordinary matter and radiation in ways we can actually study observationally and constrain quantitatively. The detailed shape of the spectral energy distribution, the physical size and internal structure of the object, the characteristic lifetime and evolutionary timescale, all of these observable properties would provide direct empirical clues about the fundamental nature and interaction properties of dark matter particles. It would effectively transform dark matter from a mysterious, invisible background component, inferred purely through gravitational effects, into something that leaves clear, measurable observational fingerprints, accessible to detailed astrophysical study. The final reason this possibility matters scientifically is fundamentally technical and observational. Webb represents the first telescope humanity has built with sufficient infrared sensitivity, spatial resolution, and wavelength coverage to even attempt detecting something matching the theoretical predictions for dark stars. Earlier space-based observatories lacked the necessary angular resolution to resolve these objects from their surroundings, and ground-based telescopes couldn't reach deeply enough into the infrared spectrum where dark stars would radiate most intensely. If dark matter stars were genuinely present during the initial phases of cosmic structure formation, they would have remained completely hidden and undetectable until Webb's capabilities became available. So the sudden appearance of these observationally unusual, theoretically puzzling objects in Webb's data, almost immediately after it began science operations, feels like a genuine, meaningful empirical test of theoretical predictions. Either the universe contains stranger, more exotic physics operating during its earliest epochs than we previously understood, or our theoretical models and interpretive frameworks need to substantially catch up with the flood of new observational constraints Webb is providing. The next steps forward are methodologically straightforward, even if technically challenging. Better spectroscopic data with higher signal-to-noise ratios, clearer detection of diagnostic spectral features, and identification of additional candidates will collectively decide whether any of these anomalous objects genuinely point toward dark matter physics, actively operating in observable astrophysical contexts. A single, strong, unambiguous confirmation would be revolutionary and transform the discussion overnight.